A magnitude 7.7 earthquake struck off the coast of Indonesia before sunrise on August 15th, and within minutes, authorities were dealing with a second threat, the possibility of a tsunami. The earthquake was not just large, it was shallow, offshore, and close enough to populated parts of Flores to trigger an immediate warning. Stay with me to the end, because the most important part of this story is not simply how powerful the earthquake was. It is what the ocean did afterward, and what scientists can learn from it. At 4:58 in the morning local time, according to Indonesia's Meteorology, Climatology, and Geophysical Agency, or BMKG, the earthquake struck in the Flores region of East Nusa Tenggara. BMKG's updated analysis placed the magnitude at 7.7, with a depth of about 15 kilometers. The epicenter was in the sea, roughly 30 kilometers northeast of Mbe in Nagakeo Regency. The United States Geological Survey also recorded the event as magnitude 7.7 and identified it as the potential mainshock of an earthquake sequence. That distinction matters. A mainshock is the largest earthquake in a sequence at the time it is identified. Smaller earthquakes can follow it as aftershocks, but scientists cannot simply assume in advance that every later event will be harmless. The shallow depth made this earthquake especially significant. When a large earthquake happens relatively close to the seafloor, it can disturb the ocean above it. But magnitude alone does not determine whether a tsunami will occur. Scientists also need to consider the earthquake's location, depth, fault movement, and whether the seafloor was displaced vertically. In this case, BMKG's tsunami modeling indicated a potential tsunami threat across parts of eastern Indonesia and nearby regions. Warning levels were issued for several coastal areas. Some locations were placed under a higher alert because modeled wave arrival times were only minutes after the earthquake. And then the instruments began recording the ocean itself. BMKG later reported observed sea level changes at several monitoring locations. At Morola in Ende, a wave height of about 0.94 meters was recorded. Other stations also detected smaller waves, including measurements at Labuan Bajo, Sika, Flores Timur, Dompu, and Alor. These observations were important because they showed that the tsunami signal was not merely theoretical. The ocean had responded to the earthquake. But there is a crucial scientific detail here. A tsunami does not necessarily look like a giant movie-style wall of water. In many cases, the most dangerous effect can be a rapid change in sea level, followed by powerful currents and repeated waves. The first wave is not always the largest. That is why authorities can continue warnings even after the first wave has passed. The earthquake happened in one of the most tectonically active parts of the planet. Indonesia sits within the complex boundary zone of several major tectonic plates and microplates. The region around the Flores and Sunda arcs experiences intense deformation as plates move, collide, and interact beneath the ocean and islands. But there is another question scientists always face after a major earthquake. What happens next? The answer is not as simple as saying another huge earthquake is coming. Seismologists cannot predict the exact time, location, or magnitude of the next earthquake. What they can do is monitor the sequence, identify aftershocks, study the fault mechanism, and compare the event with the surrounding tectonic structure. For the people living near the coast, that distinction can be critical. A warning does not mean a catastrophe is guaranteed. It means the available evidence is serious enough that protective action may be necessary. And this is where the story becomes even more interesting. Because the first danger was visible in the earthquake data. The second appeared in the water. But the biggest scientific question remained underground. Exactly how did the fault move? And how much of the seafloor shifted during those few seconds? That answer could help explain why the tsunami signal appeared, how the earthquake sequence develops, and what scientists should watch for next. But what followed the mainshock may reveal even more than the earthquake itself. In the hours and days after a major earthquake, researchers watch the pattern of aftershocks like a fingerprint. Their locations can outline the part of the crust that ruptured and help scientists understand how stress was released. It is not a crystal ball, but it is one of the most useful tools available for studying what happens after a major rupture. The answer to that underground question begins with something scientists already know about Flores. This is not the first major earthquake to strike this region. In 1992, a magnitude 7.8 earthquake occurred in the Flores region. It generated a destructive tsunami and became one of the deadliest earthquakes in the area's recorded history. USGS records show that the 1992 earthquake killed or left missing at least 2,200 people. The disaster struck Malmare and other communities across the Flores region. The earthquake itself caused severe damage, but the tsunami made the event far more devastating. That historical memory matters now because the 2026 earthquake occurred in the same broad, tectonic environment. But history does not mean repetition. Scientists cannot say that a 1992 scale disaster is about to happen again. A large earthquake does not automatically trigger another earthquake of similar size, and there is no scientific method that can predict the exact time and location of the next major earthquake. What researchers can do is study the aftershock sequence and the geometry of the rupture. The USGS identified the August 15th magnitude 7.7 event as the potential mainshock of an earthquake sequence. Its database lists dozens of earthquakes associated with that sequence. Each new event gives researchers another piece of information about where the crust is adjusting after the main rupture. Think of the crust as a huge, stressed mechanical system. For years, tectonic forces can slowly deform the rocks along a fault. Then, when the accumulated stress exceeds the strength of the fault, the rocks suddenly slip. That slip releases energy as seismic waves. The main earthquake is the largest release in the sequence, while aftershocks represent additional adjustments around the ruptured area. This process can continue for days, weeks, or longer. The important point is that aftershock activity does not provide a countdown clock. A sequence can gradually become quieter, but scientists cannot look at a declining number of earthquakes and announce that another large earthquake is impossible. They monitor the rate, size, depth, and location of the events instead. The tsunami question is equally important. The 2026 earthquake demonstrated why coastal communities need rapid warning systems. The earthquake occurred offshore, and tsunami monitoring became an important part of the response. For people near the coast, the practical lesson is simple. When a major offshore earthquake occurs and authorities issue a tsunami warning, people should follow official instructions immediately rather than waiting to see a wave. And there is another reason scientists will continue watching this sequence closely. Earthquakes can reveal the structure of faults that cannot be observed directly from the surface. By comparing the locations and depths of aftershocks, researchers can estimate where the rupture propagated and how stress was redistributed through the surrounding crust. Over time, these observations can improve hazard maps and earthquake science. They cannot prevent earthquakes. They cannot tell us the exact date of the next one. But they can improve our understanding of where the greatest risks are and how quickly communities need to respond. As for what comes next, there is no credible forecast saying that another magnitude 7 or larger earthquake will definitely strike Flores on a specific date. Any video claiming to know that would be going beyond the evidence. Instead, scientists will keep watching the sequence, monitoring seismic activity, studying tsunami observations, and updating assessments as new data arrives. The story of this earthquake is therefore not a prediction of the next catastrophe. It is a reminder of how quickly the Earth can release enormous amounts of energy, and how much information scientists can recover from the seconds that follow. Flores has experienced this kind of danger before. The 1992 disaster showed the consequences of a major earthquake, combined with a tsunami. The 2026 event gives scientists a new sequence to study, and coastal communities another reason to take earthquake and tsunami preparedness seriously. For now, the most responsible conclusion is also the simplest one. Watch the data, trust official warnings, and do not confuse scientific monitoring with prediction. This earthquake has already happened. What happens next cannot be known with certainty. But every aftershock, every seismic measurement, and every ocean observation adds another piece to the puzzle. And that is exactly why scientists will keep watching Flores.